First of all, what can we do with the transfer matrix? The two-dimensional lattice. I will take P sides over Q, N is PQ. This is the number of sides. 1 to P, 1 to Q. Can one define a transfer matrix? The answer is yes, but the price to pay, you will see, is high. I can, for instance, define the transfer between this line and this line. So the spins on this line, I will call them sigma. The spins on this line, I will call them tau. But sigma, it's not one spin, it's sigma 1 up to sigma q, and tau is tau 1 up to tau q. So I can define a transfer matrix of the set of sigma and the set of tau, which is something like exponential beta j sum 1 to q sigma a tau a. These are the verticals. But I have also to take the horizontal. So the horizontal will be exponential beta j sigma a plus 1. And I could stop here, but I prefer to make it symmetric. Plus tau a plus 1. And then I've taken this. And the partition function is trace of this matrix T, if I take periodic boundary condition, to a power P. Because I repeat that 1, 2, P times. Okay? So this is, again, transfer matrix. However, what is the size of this matrix? I've taken 0 field. What is the size of this matrix? Well, it's a number of variables here. Each one takes 2 values. So it's a matrix which is 2 to the q by 2 to the q. And P and Q is of order square root of n. So first of all, we diagonalize. Diagonalizing such a large matrix is not something that we can do at breakfast, even at lunch. It's a huge matrix. Second, we see that maybe there is a way out of the Perron-Frobenius theorem, because as long as Q is finite, the matrix T is positive entries. The eigenvector of largest eigenvalue is single, non-degenerate. So lambda 1 is always greater than lambda 2, it's not degenerate. However, nobody tells me that when n goes to infinity, the size of the matrix changes, the distance between the two eigenvalues can change with Q, and maybe will go to 0 when Q increases. So one sees that in the thermodynamic limit, there may be a possibility of having and infinitesimal degeneracy between the two largest eigenvalues. So because this matrix has a size which goes to infinity with the volume, we cannot use the Perron-Frobenius theorem to assert that in the thermodynamic limit there is a gap. The gap may vanish. I'm not going to diagonalize this matrix to find the eigenvalue. It has been done. It's a historical solution by Lars Hansager, 1940 something. 1941, something like that. And the spontaneous magnetization was computed exactly by Young. Many years later, it's in the 50s. It's a triumph of mathematical physics, and this exact solution has inspired many development of physics since then. However, the minute you change a little bit, there is no solution. For instance, if you added a magnetic field, nobody has been able. There is no solution. It's not known. If H is non-zero, the solution is not known. And needless to say that in 3 dimensions, where we could do the equivalent, transfer from plane to plane, no exact solution has ever been found. So we will have to find other methods to treat physics which is 3 dimensions at the end of the day. Now, before Hansager, Piles without solving showed that there is a non-zero magnetization, or if you prefer, spontaneous symmetry breaking in the system. He gave a proof of it before the model was solved. And this is how, for the first time, we could see that the principle of statistical physics allowed for phase transition. So I'm going to prove this for you. It's a delicate proof. It's mathematical physics. It's the only time I will do mathematical physics with you. The rest of the time will be much simpler physics. If you don't like it, you can forget about it. But if you want to know what's mathematical physics, you will see it once, and after that, no more in our lectures. So I will do it once. It will take probably the rest of this morning, but you will see what it means. So I take 2D, zero field, but I will take boundary condition in which the spins are frozen on the boundary to be plus everywhere. The configuration is a set of plus and minuses, etc., everywhere. This is one configuration C. As we know, there are 2 to the n configuration. And for configuration C, I will call n plus of C the number of spin-up, n minus the number of spin-down. Of course, n plus plus n minus is n.
Let me look at my notes to be sure to do things in the right order.
If I want to calculate the mean value of sigma, it's of course 1 over n because translation invariance. And this is such simply for configuration C, this is plus n plus time minus n minus time expectation value, meaning average with Boltzmann weight on all configurations. And I can eliminate n plus, which is n minus n minus, and I find 1 minus 2 n minus of C over n. So if I can prove that this ratio is smaller than 1/2, I win. If you can prove that this ratio is bounded by 1/2, then I've proven that there is a spontaneous magnetization. Okay. So let's go on with our configuration. I will blow a few more spins, etc. I can draw my configuration like that. I will surround the downspins by a polygon which separates the downspin from the upspins. So configuration C is equal to a set of polygons. If I have C, I can draw polygons. If I have polygons, I can find C. If I draw a set of polygons like this, sorry. I start from the boundary, and I know that I mean that here outside they are all plus, inside they are all minus. The situation may be slightly more complicated. I can have a situation like that. Here's the lattice. Then the spins will be plus here, minus here, but plus again here. That's possible. I will classify polygon by that perimeter. B. The PB means this is a polygon of perimeter B. For instance, this one has perimeter 4, 1, 2, 3, 4. This one is 1, 2, 3, 4, 5, 6. This one is 1, 2, 3, 4, 5, 6, 7, 8. Okay? So there are many polygons of perimeter B. For instance, there are many polygons of perimeter 4. I will call them J. J will tell me which polygon of perimeter B I talk of. I will rank them arbitrarily. For instance, if B is 4, the polygon is just a square. And this square, I can put it anywhere on the lattice, so J takes about n values. I decide where I put this left corner. So configuration C is given by a set of polygons. I have a polygon of perimeter B1 of number G1, B2, G2, etc. This is a configuration C. Next, I will define, it's useful, a characteristic function, which I will call chi bj of C, which is equal to 1 if p bj belongs to C and 0 otherwise. Good. N minus of C. Is smaller to some, maybe equal, of chi bj of C times n bj, n bj is the area, the number of spins inside this polygon. Why is it an inequality and not an equality? I'm saying to calculate n minus, I should count how many downspin I have in every polygon, provided this polygon belongs to C, which is what this chi function is telling me. It's an inequality because sometimes, as I proved earlier, you can have a situation like that, in which here I'm counting as minus, and I'm counting in those as minus, but in fact they are pluses. So it's an inequality and not an equality. It doesn't matter, I want to bound. Okay. NBJ. Is the number of sides into a polygon of perimeter B. How many sides are there inside? Well, first of all, I can, without changing the perimeter, I can transform this into a rectangle. This would be smaller than the number of sides in this rectangle, which has the same perimeter. And then, since I want to bound, I have a rectangle of perimeter B. What is a bound for the area of a rectangle of perimeter B? Well, the area is smaller than the square. The largest area is given by the square of length B over 4. The area of the rectangle is smaller than the area of the square. No? Is that obvious to you? Yes, you know that. So NJB is always smaller than B over 4 square. That's simple. Next, I want to define nu, the same notation of B is the number of polygons of perimeter B. How many are there in this class? For instance, nu of 4. How many square can I put in a lattice? Is essentially n. There's problem at the boundary conditions, but at the boundary, but it's certainly proportional to n. Nu of 6 is approximately 2n. Because 6, I can have a rectangle like that, or I can have a rectangle like that. And then I could put them anywhere on the lattice. Nu of 8, it's much more complicated. Because I can have 8 as 2 squares, or I can have 8 as like that. If I take 2 squares, this is of order n squared 1/2, because they are equivalent, and then there is a term proportional to n, and this is difficult to calculate. So these numbers are difficult. However, all I want is mistakes. I will take connected polygons of perimeter B. So this is not allowed. I want to calculate how many connected polygons of perimeter B, so then nu of 8 would just be proportional to n. I made a mistake. So I count how many polygons connected of perimeter B I want. So I want to find a bound on mu of B. So here is my connected polygon. I want to count how many polygons of that shape I can make on the lattice. Well, I can choose to put this point anywhere on the lattice, and then I draw my polygon. So I choose an origin, they are n-side. And then I will build my polygon stepwise. I choose the first step, and then I cannot go backward, I can go forward, this way, I have three possibilities. So I choose this one. Here I have again three possibilities. I choose this one, again three possibility, etc. So the result is that this is smaller or equal to 3 to the b, or rather b minus 1, because at the end I have to come back. So again, here I'm counting a bound on number of polygons of perimeter b that I can draw on a lattice. N is where I put it, and this is for its shape. The shape can vary with B. For a given B, I can have many shapes. For instance, I could have this one. This has perimeter 8. This has perimeter 8. So this counts all possible shapes. Okay, now we can start. N on the top, raise this. And I calculate the expectation value of n minus of c. Smaller equal to this, which is sum of b. This I replace by its bound. And here I have the expectation value of, chi j b of c. Chi j b of c means the following. So, what did I do? I calculated this expectation value. This expectation value is an expectation value of something which was 1 if C contains this polygon, 0 otherwise. So I count here the Boltzmann weight, normalized, with all polygons of which contains P for all configuration, which contain one given polygon. So this is where we concentrate on. I need that. Good. So I want to calculate sum over C exponential minus beta E of C, in which C contains explicitly one frontier divided by sum over C of exponential minus beta E of C, which is the partition function itself. This is this ratio that I need to calculate. So somewhere in my configuration, I have one polygon, this polygon, and many others possibly, but all I know is that I have this polygon. To this configuration, which contains this polygon, I will associate the configuration C star, in which this polygon is absent. The rest I leave, but this is absence, which means that all the spins which were minus become plus. Okay? So let me compare E of C star minus E of C. In C star, in C, I had spins which were across the boundaries. Therefore, I had an interaction which was plus J in C, I'm sorry. In C, I had an interaction which was plus J everywhere, because the spin, remember that the energy is minus J times sum on sigma, sigma prime. So when the spins are opposite, I get a plus J, and in C star, I get a minus J, because I've erased these spins are the same. Therefore, I get a difference of energy between C and C star, which is minus 2J times the perimeter. Because when I reverse the spin from minus to plus, inside it's the same energy. It's only at the boundary that the energy changes. Because inside, whether they are all plus or all minus, it's the same. Therefore, this is smaller or equal to I can replace this ratio by exponential E of C star. E of C star is E of C, which will disappear, minus 2bj, so plus 2jb. No, minus here. C over C star, C, E of C is E of C star, plus, yes, plus 2bj, so let's keep this. So where do we stand? Expectation value of n minus of C is smaller, sum over B, sum over J, E over 4 square, and here this ratio, we have found a bound which is exponential minus 2jb, which is smaller, sum over b, b over 4 square times mu of b, times exponential minus 2jb. And nu of b, I know that it's bounded by n 3 to the b minus 1. And b goes from 4, 6, etc., up to the largest polygons, which is for the 4n. So we end up, after this complex calculation, with N1 I've forgotten beta here. Boltzmann weight at the beta. And I can go from 4 to 6, and then since I'm looking for an upper bound, I can go from b up to infinity, provided the series is convergent. Is it convergent? Yes, it's convergent if 3 exponential minus 2 beta j is smaller than 1. This is a convergent series. So the right-hand side is a function of beta, the temperature. When the temperature is large, beta is small, this inequality is not valid. 3 is not smaller than 1, beta is 0. So it's certainly not valid at high temperature. At low temperature, beta is large. Beta is large, this inequality is satisfied. If beta is large, this is a function of beta which decreases when beta increases. And there is a temperature beta star There's a temperature beta star at which this sum is equal to 1/2. It certainly exists because when beta increases, this is a monotonously decreasing function of beta. Therefore, for beta greater than beta star, or t smaller than t star, there is spontaneous symmetry breaking. So this is the mathematical proof. You see that it's painful, difficult, it's mathematics. If you don't like it, I don't like it, don't do that. If you like it, this is what mathematical physicists do. Prove theorem whenever it is possible, but this theorem historically proved that there was spontaneously symmetry breaking for the Ising model in 2 dimensions. We will stop for 5 minutes, and then we will, instead of doing mathematics, we will do simple argument to understand what we have done. Okay? So this is the end of mathematical physics. No more. but the proof, you find it in the notes if you want. I want a simpler argument. So I start at 0 temperature. I assume that the system is all up everywhere. Then, when I go to higher temperature, the energy will increase. But the entropy increases. And therefore, we have to study, as we said in the very first minutes of these lectures, we have to study the competition between energy and entropy. So I want to see what happens if I want to create a big bubble of opposite spins inside. If this linear dimension is square root of n, I'm in 2 dimension, I take a linear dimension L, which is of order square root of n. This is the linear dimension. This is some dimension L of order square root of L, so that there is a finite fraction of spins which are minus. How much energy does it cost? How much entropy to make such a bubble? Well, the energy is simple. If I compare this to the ground state, which was all plus, those spins have not changed. The spin inside, no change, because minus minus and plus plus is the same. The only difference is the boundary. So the energy increases by a factor which is 2J multiplied by the perimeter of the bubble over L. And if I was in dimension D of dimension D minus 1, the area, it would be a sphere in 3 dimensions, and the area of the interface would be L squared. This is dimension D. What about the entropy? So let's go back to dimension 2. The entropy is the number of ways of putting these bubbles. Log of the number of ways of putting this bubble, which is n, because I can choose this point and move it around in n possible ways. And then I have to count how many bubbles, how many loops I can make of perimeter L. Any loop with a perimeter of order L would give the same energy. How many such loops? Well, that we counted. It's random walks. How many walks I can do? In 2 dimensions, I could have here 3 choice L times. Because if I want to make a loop, I start, I go somewhere, then I have 3 possibilities, 3 possibilities, 3 possibilities, and I do that L times. So the entropy is something like log n 3 to the L. Log n is not interesting at all, because log n in the thermodynamic limit compared to L, which is of order square root of n, is negligible. However, this one, the second one, is L log 3. So we see that the energy goes like L, and the entropy goes like L. Therefore, if I do E minus Ts, I see that at some temperature, the entropy will win compared to the energy. When the temperature increases, this term finally will be larger than this one, and therefore the entropy will win and we'll get a disorder. You see that this is exactly what went into this proof. A very complicated proof, very difficult. But really, the central part was compare the energy of C. The central equation was C star minus the energy of C. All the rest was junk. It was really comparing, calculating the energy of making a bubble of opposite spins. So, here, let's compare one dimension. Let's do this argument in one dimension. Here I make plus, here I make plus. So I want to calculate, make bubbles. I make a bubble. The energy is 2J. The entropy is 2J, no, it's 4J. Because it costs 2J here and 2J here compared to the ground state. The entropy is how many ways I can move these bubbles. Well, log n. So this is always the entropy wins. This is finite, this is much larger. And therefore the system has interest to create bubbles. In fact, the system will create many bubbles. What happened in one dimension is that even at infinitesimal temperature, the energy is very small. It's just the number of points where I've made this. The entropy is considerable because I can move all these squares in all possible ways. So, the lower critical dimension, I said earlier that this was d minus 1. The lower critical dimension is equal to 1 for a discrete symmetry, meaning that no spontaneously broken symmetry in less than one dimension, but there is spontaneously symmetry breaking above 1. And we will apply the same heuristic argument to understand continuum symmetry. We will see that with continuum symmetries, we have to be in more than 2 dimensions. So I take the example that we had earlier of vectors with nearest neighbor couplings. So I will assume a ground state in which everywhere in the system all the vectors point parallel like that. This is the lowest energy state. Energy was minus J sum over neighbors. SI is J. So So this is my ground state, and my boundary condition have chosen this ground state among all the possible ones. There are other ground states. For instance, there are ground states in which the energy, the spins could be rotated by an angle theta. This is another ground state. This angle is theta. So there are many ground states. So I will ask a similar question, starting with my up pure state. Can I create inside a bubble in which the spin would be rotated at an angle theta compared to the ground state? I want to calculate the minimum energy required for going to vertical to theta. So I will do an auxiliary problem, which is here. I have here something like L state. Here my spins are like that. Here my spins are like that. This is an angle theta. What is the minimum energy? What are the configuration of minimum energy which allow me in L state to rotate from this to this? Well, you could say I will assume that somewhere, for instance here, somewhere there is, here they will be all like that, here they will be all rotated. That's one possibility. What would be the energy for that? The energy, the constant energy would be J cosine theta multiplied by the number of spins in this. Well, I'm in 2 dimensions, so this is n is equal to m squared, n by n. So it's m times j cosine theta. Okay, this is the energy that it costs from going to, no, I'm sorry, 1 minus cosine theta. Okay, I have to compare the energy for the ground state, which is minus j, to the energy for the rotated state, which is minus j cosine theta. So the excitation energy is minus j cosine theta plus j. So I have to pay an energy which is, this is higher than this one, which is this multiplied by the number of spins, which is m. So that's one possibility. Is that the lowest energy to pay? Well, no. In fact, this is not what happens, because let's compare if what we would do if we rotated here by theta over L, here by 2 theta over L, and finally 3 theta over L, finally arrive at theta after L step. I rotate progressively. So if I take if I take now two nearby region, the energy goes from minus j cosine theta over n theta over L to minus j cosine n plus 1 theta over L. And if L is very large, it goes like delta E goes like theta square over L square, which is the difference between these two, multiplied by the number of spins, which is L here, in the line, which was M, and this L times, because I rotate L times. Therefore, this progressive rotation requires, since L and M are all of the same order, an energy and delta E of order 1, whereas this is much higher. So the lowest energy to spend for go to here is by a progressive rotation. So my bubble will be accompanied by a progressive rotation from here to here. And you see that the constant energy, delta E, for making the bubble in 2 dimensions is of order 1 in the larger limit, L m over L squared. Whereas, of course, the entropy is large. Therefore, for a continuous symmetry, we are in the same situation as we found in the Ising model in 1 dimension, in which delta E was order 1 and S was large. Here it's the same. Delta E is of order 1. You should repeat my calculation slowly to do it better, but you will see that the configuration of lowest energy is a continuous change from one to the other, and you will see that delta E is of order 1, and therefore, in 2 dimensions, the order is destroyed. So in this case, the lower critical dimension is equal to 2. There is no spontaneous symmetry breaking in 2 dimensions. And again, there is a rigorous proof, which is due to Mermin Wagner. And in field theory, there is a similar proof by Coleman, which says that in 2 dimensions there are no Goldstone bosons, but it's exactly the same statement. Therefore, for continuous symmetry, there are phase transition, there are spontaneous symmetry breaking if D is greater than 2. Does that mean, I will leave you soon, does that mean that in 2 dimensions there are no phase transition with continuous symmetry? Well, there is a curious case that you should know that I will not describe here. There is a curious case in 2 dimensions So 2D, no spontaneous symmetry breaking, no long range order. However, this is for continuous symmetry. There is a case n equal 2. Case n equal 2 is very simple. The other parameters vary on the circle. And again, the energy is minus J sum of Si Sj nearest neighbor. This model has been solved by Kosterlitz and Saulus. Beautiful solution comes from the normalization group that you have seen but that we will see again. And what happened is very curious. There is no Lagrange order. The expectation value of S is always 0 at all temperature. However, if one looks at the free energy, it's analytic for T greater than Tc. It's analytic for T lower than Tc. Here this function I will call f plus. Here I will call it f minus. F plus is analytic in this domain. F minus is analytic. These two functions at Tc are equal. As well as all their derivatives. However, they are different analytic functions.